I'm going to work out a couple examples from section 8.1, which is about systems of linear equations. So you got two equations in this section. They're both linear, involving the variables x and y. Those are the unknowns. And we want to find a solution, which is going to mean an ordered pair x and y, which is going to simultaneously solve both the first and second equations. Now we know that the graph of a linear equation is a straight line, and therefore, graphically speaking, we have this situation. Either the lines corresponding to each equation intersect in one spot, which in that case you have one solution. That's the typical situation. Or the lines are parallel to one another, and therefore there is no solution. Okay, because a point is going to satisfy both equations if and only if it's on the graph of each line, and that can happen only if they intersect each other. The oddball case is when each line or each equation corresponds to the same line when you graph it, in which case you have a whole line of solutions. Okay, we're going to work this example out. So we want to solve this system from the handout. X plus 2y equals 2, negative 4x plus 3y equals 25, and we're going to do it using the two methods. One is substitution, the other is elimination. With substitution, what you want to do is solve either one of the equations for one of the variables, either x or y, and then substitute that expression into the other equation for the variable you solved for. Alright, now looking at this system, it's pretty clear that the first equation is going to be easiest for us to solve that equation for x. So that's what we'll do. We'll solve the first equation for x and then substitute that expression into the second equation, and then eventually solve for y. Okay, so to solve the first equation for x, we're going to just subtract 2y from both sides, and that gives us x is equal to 2 minus 2y. What we want to do now is take that expression and substitute it into x in the second equation. Right? Hence the method, the name of the method is substitution. So we get negative 4 times our quantity for x plus 3y equals 25. That's the second equation of our system. Now we're going to substitute in for x 2 minus 2y. That results in one equation with one unknown. To solve for y, we're going to distribute the negative 4 through to get negative 8 minus or plus 8y plus 3y, and that equals 25. And combining like terms there, we're going to get 11y, or minus 8 plus 11y equals 25. And then we do the usual when we're solving for linear equations. We isolate the variable, add 8 to each side to get our new equation, which is 11y equals 33. Divide both sides by 3, and then we get our y-coordinate of our intersection point, which is y equals 3. Now to solve for x, we can plug in x equal or y equals 3 into either equation, or just plug in y equals 3 into the equation we got by solving for x. Alright, so that's going to give us 2 minus 2 times 3, 2 minus 6, which is negative 4. Okay, so putting this together, we got an ordered pair. Okay, the x component's negative 4, the y component's 3, so the solution to our system, it's got to be an ordered pair. X and y is negative 4 and 3. That solves the system of the equation. So that means we plug in negative 4 for x and 3 for y into each equation. They will both be satisfied at the same time. Okay. Now the second method, the substitution method, or sorry, the addition or the elimination method, has as the following approach. What we're going to do is look at our system and that we started with and multiply one or possibly both of the equations by numbers, possibly different numbers, with the idea of adding the results together to get one of the variables to cancel out. Okay, so for instance, looking at this system here, and we're starting with, we see we've got a negative 4x here and an x. Well, if this was really a 4x here, then we would have 4x plus negative 4x, which would cancel out to give us 0. So that's the idea. We're going to multiply the first equation by positive 4 to make the coefficients of x opposite to one another to get them to drop out. Okay, now we only have to make only have to multiply the first equation by a number. In this, for this system, for other systems, you might have to multiply each equation by separate numbers to get one of the variables, x or y, to drop out. Okay. Okay, so let's just rewrite the system down below. And then we're going to multiply the first equation by 4. Okay, now that's just for convenience sake in this case. We could get the y's to cancel out, for instance, by multiplying the first equation by 3, the second equation by -2. But this is just the easiest way to go for this system. Distribute the 4 through. Don't forget to do that. We get 4x plus 8 on the left equals 4 times 2, which is 8 on the right for the first equation. Just rewriting the second equation, we get this. Now, if both sides are equal in each equation, when we add them together, we must get a valid equation. So in this case, we get the x's to drop out. 4x and -4x add up to 0. 8y and 3y give us 11y equals 33 on the right. So just like before, no surprise, we get y equals 3. Now, with the addition or elimination method, we got to go and plug in y equals 3 into either one of these original equations from our system. So I'll just plug it into the first one. Plug in y equals 3, we get x plus 2 times 3 equals 2. So it's x plus 6 equals 2. Solving for x, we're going to get x to be -4. So we get the same ordered pair as we got using the substitution method. So you pick which one you prefer when you're working out these kinds of problems.